Today is like a revision. It's a revision lesson of what we have done in the last 4 lessons. So in the last 4 lessons, we have done about nitrogen and its compounds and sulfur and its compounds. And today we are going to do a lesson to put all that together and to see how we answer the examination questions. And you can have a go at the examination questions today. So here we go. Let's see if I can find it. Okay, so today's lesson is about the sulfur and nitrogen chemistry, and I'll tell you how it goes, but it is a knowledge check lesson. And the idea of these is to try to make sure, hello, St. Mary's, how nice to see you. You have not missed anything yet, which is good. It's a knowledge check lesson. It's a chance for you to have a look at something, see if you can answer the questions. Here are a few tips about learning, though. Firstly, when you have a lesson in any subject at your school, it is worth making some short notes immediately. To have some revision book or pieces of paper or something where you can write down stuff straight away. They say that if you try and look at a piece of information 1 day later, 1 week later, and 1 month later, you will always remember it. Now, this is too simple, but the idea is right. That you try to see something, like I try and learn something 1 day, and I look at it the next day to remind me, then 1 week later, then 1 month later, and I don't need to do very much work. I just need to look at it. Revise means see again the next day, next week, next month, and then I won't have to remember. It won't be difficult to revise for the examination. Do a lot of testing with a friend or a partner in the classroom. Do set up little tests for each other. Do, very, very important, use past examination papers and their mark schemes. The mark scheme is very important. You need to know what the examination expects you to be able to write. And the last thing is don't get lazy. Do not think, I'll do that next week. I'll do that sometime. I don't worry now, it'll be okay. Don't do that. Try to make constant revision, always making a few notes, always after lesson. Try to remember things. Look at them the next day, 1 week later, 1 month later. Do testing with each other. Do use past examination papers. It is easy to see examination papers on the internet and mark schemes. There are many, many copies of them out there. And do not get lazy. I'll tell you how today's lesson is going to go. I will show you something that we have done in the last 4 lessons, and we will look at it, and then I will show you some questions. And what I want you to do is to have a good look at the first piece and then to try the questions. So the first one is about sulfur and its extraction. So in the lesson about sulfur, we came across this. Now in this is the Frasch process, down at the bottom, the Frasch process. And there were 3 pipes, one inside the other. In the middle one, we put hot compressed air, goes down. In the outer one, we have superheated steam. Some of them say superheated water, doesn't matter. It's steam. And in the middle one, molten sulfur and water comes up. So the pressure comes from the air, the melting comes from the superheated steam, it melts the sulfur, and that gets blown up like a foam out of the top. So it's called the Frasch process. And what you need to do is to try to remember what is in each pipe, what the process is called, and how it works. Okay? So let's have a look at a question so you can see. So I'm going to give you just one moment more to look at this, because this is how this lesson is going to work. So here we go. There it is, 3 concentric pipes. So there's one, and then another one outside it, and then another one outside that. So in the first one, compressed air. In the second one, the sulfur is coming up. In the third one, the superheated steam. And that helps to keep the sulfur molten. So here's the question. Have a look at the question. See if you can answer the question. Sulfur is extracted from underground deposits by a process in which 3 concentric pipes are sunk down to the deposits. There it is. So we've got J, K, and L. J is the middle one, K is the outer one, and L is the middle one. Name the process, what is put down J, and name the allotropes of sulfur. Now, it might be worth you just writing those questions and your answers to them, and then we'll see what you know. Okay, so I'm going to give you a few minutes just to have a go at that. Everybody have a bit of a go at that. Are you going to have a go, Kabiro? I can see St. Mary's is thinking about it. Mathari is writing about it. That's very good. It's nice to see people actually working. Well done. Kabiro, have you got your answers? Everybody should be trying to do it themselves, not waiting for the cleverest person in the class to do it. Everybody needs to try and do it themselves. That is correct for the first part, Kabiro. Well done. Now, what about B and C? So A, what is the process called? What is put down pipe J? That's the middle one. Hot compressed air, Mathari. Frasch, very good. And the 2 allotropes. Now, we haven't done the allotropes of sulfur today. Excellent, Mathari. Very, very good. Well done. Kabiro, I'm going to have a look. A little bit closer, please. No, the middle one. Very good, Usharika. Well done, Usharika, for the allotropes. Excellent answers. St. Mary's wants to show me a little bit again. Look at this again. Look, here's the question. Right, we're going to go back. What's down pipe J? J is the one right inside. Here's the diagram again. Ah, do you see the one right in the middle is hot compressed air? Now, I think many people got the Frasch. That's very good. What is put down pipe J is hot compressed air. And the 2 allotropes of sulfur, everybody think again, because some people got it, some people did not. What are the allotropes of sulfur? One starts with M and one starts with R. Really good, Kabiro. Really good, Usharika. Very, very good. Okay, so here are the answers. If you weren't sure, here it is. It's the Frasch process. Try to spell it correctly. It's SCH. It's a German word. Frasch process. It's hot compressed air, and there are the monoclinic ones, which look like needles, and then there's rhombic. Here's another question, which is very similar. Look. There it is. This is like a cross section, like they've cut through it. And there's tube 1, tube 2, tube 3. What's in 1, 2, and 3? And don't worry about question 5, the property of concentrated sulfuric acid. We will look at those later. Okay, we will look at those later. But which is it? 1, 2, and 3? What is in them? I hope you know now. What's in 1, 2, and 3? Okay, so in this one here, 1, 2, and 3, they will be hot compressed air, then the molten sulfur and water comes up, and the outer one is the superheated steam, which has to be under pressure. Okay, don't worry about these two. We will look at those later. Okay, here's something else. This one was about when we were doing about nitrogen. This is about ammonia and its oxidation. Here's the piece of information which we're going to look at first. Okay, here's the information we're going to look at first, and I'm going to remind you of this. Okay, so this is a little video which we looked at when we were doing nitrogen, and I want to point out what we have here. We have concentrated ammonia solution in the bottom. We have a tube here that air comes in. It's actually oxygen, but it could be air, and it goes in down underneath. This tube here up on the left is towards a vacuum, so the vacuum pulls the air through. In the middle is a piece of platinum, which is a catalyst. So let's see what happens. You may remember this from when we did it before. So it glows. So here we are. There's the ammonia. Air is going to come through down through here, oxygen, and that's the platinum. Now, to get it to go, we have to warm up the catalyst first. But when the catalyst is warmed up, look what happens. I'm going to stop it there just for a minute. Just look at this. What is happening here is that you can see that the bit of catalyst is really hot. It stays hot. If I just heated it in the Bunsen and then I left it, it would go cold. But here it's staying hot. And I can also see, I'll just start the video again a little bit, and you will be able to see some white fumes coming. See that? See the white fumes forming? And there's the catalyst, it's very hot. Now what's happening is this equation here. NH3, O2 forms NO and H2O. Okay, NH3, O2, NO, nitrogen 2 oxide, and H2O. Now I just want to look, if you remember last time, we were looking at oxidation numbers. Let's just look at this just for a minute. So I've got NH3. Oh, it might be better if I write here. NH3. Now in NH3, because each hydrogen is +1, that means the 3 hydrogens are +3. That means that the nitrogen here is -3. When it forms NO, the N, because the oxygen is -2, the nitrogen must be +2. So the nitrogen is going from -3 to +2. And when we go up in oxidation numbers, that is oxidation. Okay, very important that when we go up in oxidation numbers, we get oxidation. When we reduce oxidation numbers, then that is reduction. And what is happening here is the oxygen is going from 0 here, that's on 0, and to H2O where it's -2. Okay, so let's just watch it again very briefly. So here it is, ammonia at the bottom, the gas coming in here, oxygen going in the side, the platinum is heated up, put inside, it would normally cool down, but it is staying hot. It is bubbling, and then we get white fumes. Look at the white fumes. The white fumes are the nitrogen monoxide or nitrogen 2 oxide. There it is, very, very hot indeed. That is because this is a very exothermic reaction. There are lots of white fumes getting pulled out there. Okay, let me just, sorry, let's just move on to the next slide. And here's a question about it. So the diagram shows the catalytic oxidation of ammonia gas. Use it to answer the questions. So this looks a bit different from that. But if you look at it, it's not that different. We've got concentrated ammonia at the bottom and a platinum catalyst, and oxygen is added. In the second one, in the question, it has oxygen coming in here from the left, not the right, that doesn't matter, into concentrated ammonia, and we've got a glass rod with a metal here. So try and answer the questions which are there. If you want to, you could write down the question, but what I'd like you to do is just write down your answers so I can see what people think. So what do you think the answers there are? What could the metal M be? And write down 2 observations. So what could the metal be? And what could the observations be? Somebody show me your answers. Observations? What's the metal? Who's going to get gold medal today? Ooh, I think it's Kabiro. Platinum. Kabiro reckons platinum, so does Mathari. Mathari came in just second. Oh, what did you get, St. Mary's? You got platinum as well. So that's gold, silver, and bronze already gone. Bad luck, Oshirika. Bad luck, Silver Spring. Very good. Well done, guys. That's very good. Platinum. Now, it can be other metals, but platinum is the most usual one. So what are the 2 observations? What were the 2 things you would expect to see? What happens inside the flask? What would I actually see happening? If you look back at the last slide, here, look, there are 2 observations. What observations do you make? A little bit closer, please, Silver Spring. It's slightly out of focus. Oh, hang on. Oh, I missed it. It's not easy to see, Silver Spring. A little bit closer, please. I'll make the picture of you a bit bigger. Silver Spring? Hot plasma reaction is tight. Yes, very good. That's one. Yes, that's one. What's the other observation? Everybody, firstly, the metal you've all got right, which is platinum. Has anybody got an answer to the two observations? Somebody from Kabiro. Two observations. Bit closer, please, Kabiro. Bit closer. And closer again, please. Sorry, but concentration of ammonia. Oh, well, no, we want what we can see. Okay, what can we actually see? Not the concentration. I want to know what happened during the experiment. Yes, actually, we do get a few brown fumes, but actually, it's not brown fumes we are looking for, Silver Spring. Yeah, let's just go back and have another look. Let's just have a quick look. Okay. So here it is. Here's the experiment. And what we're looking for, look, here it is. It goes in. And firstly, the metal stays hot, or the metal glows very hot. And look, white fumes. We do get some brown fumes as well. We do get some brown fumes, but the most important, look at all that white going up there. That's all condensed white fumes, okay? So there it is. Now you can see it going a little bit brown, and we'll look at why it goes a bit brown, but that's the main two observations. So the two observations are the wire glows red or white hot, and we get white fumes. You don't have to say what they are, but they are nitrogen 2 oxide. Okay, here's another version. Look, sorry, there we are. That's platinum. It could also be nickel or palladium. They're also okay. So the wire glows red or white hot and we get white fumes. It's okay to say we get brown fumes, but they don't come immediately, the brown fumes. They come more when it cools down. Here's another one, and it's exactly similar. It's another question, only this time they're putting the ammonia into the tube on the side, and then they've got hot nichrome, that's nickel chromium wire, but it's the same thing. Write an equation. Can anybody remember the equation? There will be this will be the platinum metal. Can anybody remember the equation for the ammonia reacting? It forms NO and H2O. Can anybody else remember the equation? I will be very interested if anybody can do this. This is quite hard chemistry. So ammonia plus oxygen gives nitrogen 2 oxide and water. St. Mary's, do you think you have an answer? Show me. Anybody? A little bit closer, please. Mathari. A little bit closer. Brilliant. That was the same. Mathari and St. Mary's. That was brilliant. You were the same speed, and you got it right. Well done. Anybody else get it right? Let's have a look. Osharika, up a little bit, please. Up a little bit, please. They're very good observations, really good observations. Up a little bit if you've got the equation. Kabiro, can I see, please? That was really good, St. Mary's and Mathari. Brilliant. Kabiro, 4546, yes. You guys are really good today. Really, really good. Well done. There's an equation for writing for the reaction that takes place. Why is it necessary to have hot nichrome wire? What is it that the hot nichrome or hot platinum is? What is it there to do? What is the metal there What is its purpose? Why do we need to have the hot nichrome wire? Good question. Who's got an answer? I'll give you a hint. The answer starts with C, the letter C. Kabiro has an answer. Come on, Mathari. Come on, St. Mary's. Come on, Osharika. What is the metal there for? Why do we need the piece of hot metal there? Mathari, are you going to go gold? Osharika are coming in really fast. Correct, Mathari. And oh, well, it's true that it's conducting the heat, Osharika. You're absolutely right. It is conducting the heat. But its main answer, the main answer, is that it is a catalyst. Here we are. There's the equation. 4, 5, 4, 6. 4NH3, 5O2, 4NO, 6 waters. And the nichrome is a catalyst. The reaction takes place on the surface of the metal, and it helps it go. The reason it stays hot is because this equation, it has, let me just add something to it, and that is delta H is negative 900 kilojoules per mole. Minus 900. Minus means it's exothermic. Okay. And 900 is really, really high. That's why it stays hot, because it's minus 900. Okay. Oh, look, now we have a question about sulfuric acid. Okay, let's have a look at it. Ah, yes, this is a simplified contact process. I'll remind you of how it goes. Okay. So there are a few reactions we have to write. At first, in number 1, sulfur burns in oxygen to form sulfur dioxide. Okay. Then the sulfur dioxide and more oxygen goes into this bit here, number 2. And in number 2, the sulfur dioxide, sulfur 4 oxide, reacts with more oxygen to form, and it's a reversible reaction, sulfur 6 or sulfur trioxide. It balances 2 of those and 2 of those. Now the temperature, it says here, is about 450 degrees Celsius. It's only about 3 atmospheres, and the catalyst, it says there, is vanadium oxide. It's V2O5. Okay, V2O5. Then the SO3 goes into here, into this big cylinder here. And there the SO3 reacts with concentrated sulfuric acid, H2SO4, to form oleum, H2S2O7. That's oleum. Then the last bit down here is that the oleum, H2S2O7, reacts with more water to make 2 sulfuric acid. Okay. So those are the 4 bits that we have to remember. Could we mute, please? Could somebody mute? Sorry about that, Al. Okay. So there are the four main parts of the contact process. Okay. So now what we'll do is to find a question that asks about this. So that's what you've got to try and remember. Now let's have a look at a question. Okay, here we go. There we are. We have a flow chart representing the main. It says drops. It should say steps in the contact process. Sometimes you will find in the examination, these are all proper examination questions. Sometimes something has gone wrong in the way they type it. It shouldn't be drops. It should be steps. Anyway, steps in the contact process. So there they are. And there are some questions which we're going to ask. The first one is, why are the gases A here and the oxygen purified? The second questions are, write an equation for the formation of oleum and what is C? Okay, so what is C there? Hot solid there. What is it? Why are the gases purified? And write an equation for the formation of oleum. Okay. So Mathari, you know something, I think. Hang on, let me just get this. To remove the impurity. Yes, that's a really good answer. Mathari, that's really good. Who's that? Yes, Sharika, you're absolutely right. And St. Mary's, you're absolutely right with that bit as well. They're really good answers. Usharika, why do they want to purify and remove the impurities? What would go wrong if they didn't do that? Yes, absolutely, to remove other particles. You're absolutely right, Kabiro. But why? What could be the problem with the other impurities? Wamawini, that's a lovely lab. It's a shame there are no students. So the first bit is, why are they purified? And most people have got an idea that it is to remove impurities. But why? Why is that a problem? Why are the impurities a problem? Somebody from Mathari got the answer exactly. And then the second and third questions are, write an equation for the formation of oleum and what is C likely to be? Good, very good, Ashurika. Absolutely. So what is the hot substance at C? We'll look at the question. We'll look at the question again. We'll look at the picture again so you can see where it is. There it is. Okay, on top right here. Up here, hot C. What is it? And can you write an equation for oleum forming? It is to remove dust particles, Kabiro, you're right. That there, part D, that is not correct. S plus O2 goes to SO2 is the very first bit. We want to know about oleum forming. So Marys, are you going to have a go? You guys are doing really, really well together. Excellent. Well done, Mathari. And well done, St. Mary's. Very good. Mathari and St. Mary's are doing really well today. Very, very good. Hello, Wamawini teacher. We've got some other schools, which is really great. We're doing some practice on nitrogen and sulfur chemistry. So I'm going to move on and see the answers. So here we are. So A and oxygen are purified to prevent poisoning of the catalyst. Some gases will block the surface of the catalyst. And let me just show you what happens. The catalyst has what we call active sites. So in the surface, there are gaps like this. And these active sites, so let's say this is the catalyst here. This is the catalyst, okay? So the SO2 and the O2 are floating around above like this. And the SO2 and the O2 get trapped in here. And then they react to make SO3. But if we have an impurity, and a good example would be hydrogen sulfide, H2S can block up an active site. And then the O2 can't, and the SO2 cannot get in, okay? They can't get into the active sites. So if we get that, if we get phosphorus oxides, they block it up, so it can't go in anymore. So that's what we call poisoning, okay? That's what we call poisoning. So these are called, it is like biology where they talk about active sites. These are called active, sites. And this is the catalyst here. The catalyst is V2O5, okay? So let's just get rid of this. Let's get rid of that. Bit of a mess. But that's how it works. It's to stop the active sites being filled up by other gases, which stop the sulfur dioxide and oxygen being able to be absorbed. Okay? Okay, next bit. Here's the formation of oleum, H2SO4, concentrated sulfuric acid, and SO3 just joined together. So now we have 2 hydrogens, 2 sulfurs, and 7 oxygens. That there, H2S2O7, that is oleum. What was C likely to be? Vanadium 5 oxide or vanadium oxide or V2O5. Okay? Okay. Next. Here's another version of it. It looks exactly the same. Sulfur goes in with air, forms SO2. Then SO2 becomes SO3. SO3 becomes H2SO4. The first one says, state the optimum, that's the best, conditions necessary for carrying out the reaction in unit 2, so for making SO3. So what temperature, pressure, and catalyst would we have in unit 2? And then stage 2 takes place in 2 steps. What are those steps? Not difficult, but it's just another question. Very, very similar sort of question. Do you see? So we are just trying to revise how to do these sort of questions. So the first one, what were the optimum conditions? Can you remember what the optimum conditions were? Sorry, Silver Spring, I need to mute you. Thank you. Wow, Mathari. Who is that? Write your name, please. I think both of you should write your name because both of you were working together. Don't you think? Mercy, just show me your answer, please. Show me the answer down a bit. Just show me the answer again, please. Look, everybody. Why is it not working? I don't know why it's not showing. Oh, it is, but not very well. Sorry. Anyway, absolutely. And Kabiro, really, really good. 400 to 500 degrees temperature, absolutely correct. What was the pressure? Mathari said 3 atmospheres, and that's correct, 2 or 3 atmospheres, only enough to just push the gases through. And the catalyst is vanadium 5 oxide. Okay? And stage two, not state 2, takes place in 2 steps. What are those steps? Here are the answers. Oh, did I not write the answers? Oh, I did not write the answers. Okay. So the optimum conditions, I'll write them now. Oh, come on. So the optimum conditions are 450 degrees Celsius, 2 or 3 atmospheres, and V2O5 catalyst. Okay, the 2 steps, stage 2, if you look back at here, stage 2 is going from SO3 to H2SO4. The first one is the production of oleum. That's the SO3. Oh, that's not very clear on there, is it? Let's do it up here. So we've got SO3 plus H2SO4 makes oleum, H2S2O7, and then the H2S2O7 has water mixed with it to make 2 H2SO4s, the one I started with and the new one. Okay, so that's the main stages. If we look, we find this sort of question very regularly. Here's another one. I'm not gonna go through this with you. I'm not going to write down the answers. Just look at it. Sulfur deposits get purified to make sulfur, which is turned into SO2, which is turned into SO3, which is turned into H2S2O7, which is turned into H2SO4. And then they ask you about step 1, 2, 3, 4, 5, like this. Step 1 is known as the Frasch process. The optimum conditions in step 3. What is A? What is B? Okay, what is A and what is B? A is here. That says what is that and what is this. Okay. And then name the process that happens in step 2. There's step 2. What is the name for sulfur to sulfur dioxide? That will be oxidation. And then we're going to look at this next bit in just a minute. Okay, this part E, we're going to look at. So don't worry about that. Okay, so let's move on. Oh, now we have a question about ammonia. Okay. Here is the basis of the Haber process. Haber, Haber process. Nitrogen, which we get from the air, and hydrogen, which we get from natural gas. Natural gas is methane, CH4. They are added together, 1 to 3, 1 nitrogen to 3 hydrogens. They go into what we call a catalytic chamber. The catalytic chamber here runs at about the same temperature as the catalytic chamber in the contact process. But this time, instead of 2 atmospheres, it's 200 atmospheres. And the catalyst could have been platinum, could have been nickel, but it's actually iron. It's not vanadium, it's iron in this case. You may notice that most of the catalysts, the metal catalysts, are transition metals, the ones from the middle of the periodic table. Then the gases are cooled and pressurized, put under pressure and cooled, and the ammonia drops out of the bottom. Now, the reason we have to get rid of that is because most of the gas is not reacted. That's because the N2 and 3H2 react via a reversible reaction. And that means that I have gas here, gas here, gas here. That in here we have nitrogen and hydrogen and ammonia. And the problem with that is that most of the gases in here are nitrogen and hydrogen. Only about 15% are ammonia. So that means that 85% stay unreacted. So the unreacted gases, the 85%, have to be recycled and go back in again. Okay, that's a very important piece of information, that because it's reversible, some of the ammonia falls to pieces as soon as it is made. Okay, really very important indeed. Okay, so here it is. Nitrogen, hydrogen, 1 to 3, goes in 450 degrees Celsius, 200 atmospheres, iron catalyst, and then pressurized and cooled makes the ammonia become a liquid so it can be removed, and the unreacted nitrogen and hydrogen goes round again. Here's a question. Here's a question. Have a go at the question. In the production of ammonia, how is the ammonia separated? What happens to the unreacted gases? Don't worry about these two down here. We will look at those another time. But these first two, what are the answers to these first two here? Very good, Wamuini. That's very good. We can all make silly faces. Can we pass chemistry, huh? Ah, yes. You see, Wamuini, I can see you. Uh-oh. Yes, we can all see you, Wamuini. Very good. But that's not the point. The idea is to try and learn some chemistry, isn't it? If you can learn some chemistry, then you don't just make money by making silly faces. You can make money by being a doctor or a lawyer or a chemical engineer or anything, be a teacher, and you can make proper money. And then you can make as many silly faces as you want. Okay, so there's the questions. In the production of ammonia, how is the ammonia separated? And what happens to the unreacted gases? Some of you might know about position of equilibrium. How will it be affected by increasing pressure? And why do we not run it at a much higher pressure? So I'm going to give you the answers because I don't want to spend too long on this, okay? Because we're running out of time a little bit. So here we go. The first one is, it is removed by putting under pressure and cooling, so it becomes a liquid. So it is being liquefied. The word is liquefied. It is spelt strangely. Liquefied. The ammonia is liquefied by putting it under pressure and cooling it. What happens to the unreacted gases? They are recycled. They go through again, go through the catalyst again. Look at the diagram. Here it is. There, the unreacted gases go round again. How will the position of the equilibrium be affected? We will do reversible reactions and something called Le Chatelier's principle. How many of you have done this? How many of you know the answer to this? Do you know about reversible reactions or no? Yes or no? So Mary's reversible reactions. Mathari, do you know? Reversible reactions, good. Okay, Kabiro, do you know? Wamuini, do you know or not know reversible reactions? Okay, so you should be able to tell me why. If we look at this, what is the reasoning? Here's the equation, N2 plus 3H2, 2 NH3. Why does that tell me that if I increase pressure, it goes that way? Why? Okay, so why does increasing pressure make it go to the right? Anybody? Does anybody know that? We haven't dealt with it today, but does anybody know why it goes to the right? That is a very good way of putting it, but why does it favor the forward reaction? That's very good, Mathari, but why? Because NH3 has very good, St. Mary's. Yes, the right-hand side has fewer molecules, fewer gas molecules. Okay, so if we look at the equation, we've got 1 and 3, that's 4 on the left, only 2 on the right. So if I put it under pressure, it will try to reduce the number of particles, which means it goes to the right-hand side. Okay, goes to the right-hand side. Why is the process not run at a much higher pressure? That's because it's too expensive. Producing a lot of pressure and having thicker tubes, because otherwise they explode, it is too expensive to have it much higher pressure. Okay, now we move to ammonia produced in the laboratory. This is one that we saw when we were doing about it. This is an ammonium salt, ammonium chloride. It could be any ammonium salt and any alkali, in this case, calcium hydroxide, and it is heated up and it produces ammonia. I'll write the equation in a minute. And the ammonia goes down the tube and it goes up because it's lighter than air. And it goes through this, which is anhydrous calcium oxide. And the ammonia collects at the top and it blows the air out of the bottom. Now, it is the same every single time. If I have, if I have an ammonium salt like NH4Cl and an alkali like calcium hydroxide, they swap places. So the ammonium the ammonium chloride becomes ammonium hydroxide and the calcium becomes calcium chloride. So we balance it with 2 of those and 2 of these, but this splits up to make 2 NH3 and 2 waters. Okay, so I'm going to simplify that. So 2 NH4Cl, calcium hydroxide, makes ammonium hydroxide and calcium chloride, and then the ammonium hydroxide makes ammonia and water. So I'm going to simplify that. Let me just get rid of that. I know some of you are writing, but don't bother. Just for a minute, let's just get rid of that. So now I can write NH4Cl plus CaOH2 goes to NH3 and water and calcium chloride. Then I need 2 of the ammonium chlorides, and I get, where's my pen gone? 2 ammonias and 2 waters. So that's where the ammonia comes from. And the ammonia goes down this tube and up through the drying agent. Okay, up through the drying agent. So that's how it works. That's in a laboratory. In industry, we use the Haber process, but in the laboratory, we use this. So let's have a look at a question. So just look at that equation. The salt of ammonium reacts with an alkali to form ammonia and water, and the metal takes the chloride from the ammonium. Here's a question. Write an equation for the formation of ammonia from ammonium chloride and sodium hydroxide. Now, they expect you to know that sodium hydroxide, and I'm sure you do, is NaOH. And then it says, give 2 physical properties of ammonia. Well, okay, 2 physical properties. We haven't dealt with that now, but hopefully you will remember some of them. There was one we looked at which had the fountain experiment and so on. So just have a go at that. See if you can write that equation. I think you can. Ammonium chloride and sodium hydroxide. You guys are doing really, really well together, students. You are very, very good today. Kabiro, have you got an answer? I see one coming forward. That's correct for if I was using calcium hydroxide. Actually, it's 2 waters. That's okay if it's calcium hydroxide. What about sodium hydroxide? Can you write it with sodium hydroxide? Very, very good, Kabiro. But the question actually asks for sodium hydroxide. We are getting towards the end of the lesson, so let's see if we can. Oh, NH4. Oh, well done, Mathari. Well done, Mathari. Is that Mercy again? St. Mary's? Show me. Can you hold it a little bit flatter to the screen? Yes. Oh no, you've suddenly made calcium chloride. Look at the end. You've made calcium chloride out of sodium. Very good. Very, very good. Well done, Kabiro. Very good answer to the properties. It has a pungent smell. That's better. That's better, St. Mary's. It does have a pungent smell and it's very soluble in water and it's lighter than air. So let's have a look at the answers because we're running out of time. Here we go. So NH4Cl plus NaOH will make NH3 and NaCl and H2O. Doesn't matter the order of them. It's NaCl, not NaCl2, and there's only one of them. And the two main physical properties of ammonia is it's very soluble in water and it has a characteristic smell. Pungent was a very good word used for it. Here's another question about the same process, and it says, explain why concentrated sulfuric acid cannot be used to dry ammonia, and what is the drying agent for ammonia? Well, we know what the drying agent for ammonia is because we just used that. Why can sulfuric acid not be used? Whenever you get a question like that, the answer is the same. If it says something cannot happen, then the answer is always the same when they say, why can it not happen? But what is the drying agent? Anybody? That's absolutely correct. Correct. St. Mary's, there should be a word in front of that. But you're right. Wamwini, down a bit, please, and a little bit further away. I can't see your writing, Wamwini. Down a bit. Oh, hang on. That's good. Calcium. Where's it gone again? Correct, Kabiro. I think that was correct, Wamwini. I think that was correct. Not hydrated. Not hydrated. No, it must be anhydrous calcium oxide. Okay, so the answer to number one is, or part A, is ammonia is a base, so it would react with the sulfuric acid to form ammonium sulfate, as somebody said at St. Mary's. And the drying agent for ammonia gas is anhydrous calcium oxide. Okay, I'm going to send this. I'm going to stop here now. I'm just going to show you something, and that is that there are some more reactions. I'm just going to show you two now. This one was the reaction of a copper coin with concentrated nitric acid. Okay, and it forms this brown fumes and a greeny blue solution. It's actually blue, but the brown fumes makes it look green. That's the first one. That's copper and concentrated nitric acid. And this one here on the right, this is sugar. It's slightly speeded up, and concentrated sulfuric acid. So the left was nitric, this one is sulfuric. This is speeded up a little bit, the video is, but it forms this black solid which comes out. It looks pretty foul, and a lot of steam and so on. Okay, now those two are both examples of concentrated acids. That's concentrated nitric on the left and concentrated sulfuric on the right. This nitric is acting as an oxidizing agent, and the sulfuric on the right is acting as a dehydrating agent. And we will look at those next time. But basically, they're about writing equations for these two happenings. Anytime you get brown fumes from nitric acid, it is being an oxidizing agent. Anytime you get an organic solid turning black, that is dehydration. Okay, that's what it's about. But that really is the end of today's lesson. So I'm going to stop sharing just now, and I'm going to stop